All right. After this, it becomes pretty easy to combine things. So first of all, let's combine the terminal condition term. So this is the only, this and this are the only term that can be combined to form a term that only depends on delta ut. So let's first write that out. U hat transpose plus partial jt partial u times delta u t. So this is the first term. Now every other thing that depends on delta u, right? Second term, this two is going to be combined to the second term, and this that doesn't depend on delta u is going to form the third term. So let's first off do the second term integration. Delta j, delta u, that's over here, and also I have a minus u hat of t partial f partial u, this guy times delta u dt, right? And as you can imagine, both term 1 and term 2 is going to be eliminated when I set the adjoint equation to appropriate values. The only term that is not going to be 0 after I enforce the adjoint equation is the third term. The third term is minus sign integration of u hat of t times partial f partial s delta s dt, right? Okay, so now this is the third term, and the adjoint equation. Let's say, what do I need to get rid of both red terms? The adjoint equation, first of all, the first term we need to make sure it is 0. So u hat at time big T, remember u hat is a function of t, right, has to be minus of partial jt partial u transpose. So what we see is that the adjoint solution has to be non-zero if the objective function explicitly depends on the terminal solution, right? So if my j objective function explicitly depends on if I have this term explicitly depends on ut, then my adjoint has a non-zero solution at the very end. So that solution is what you enforce. That solution is what you start with, and then you integrate the adjoint equation, which is what makes this 0. So you have, oh, sorry, I think I missed this, right? So there is also another term 2. Yeah, sorry. This that comes out of integration by parts is what I missed. So there is another term that it depends on delta u. Sorry. This term is minus du hat t dt delta u dt. Right? Did I miss any other terms? Right, the term we just use integration of parts to derive, I forgot to include in the second. Okay, so the adjoint equation is going to be du hat. Actually, let's take the transpose of the whole thing because I don't want to transpose in the time derivative. Du hat dt has to be equal to, first I have this, which is df du transpose times u hat, right? The transpose of the product is the product of the transpose while switching the two terms. And minus, oh sorry, this term is minus. This is, yeah, the dj du is plus. Right, so this equation is what's needed to make the delta u term in the integral to be completely 0 for any delta u, right? Okay, so now it's just like what we had in the discrete case of backpropagation. we need to solve this adjoint equation backwards in time. Because we don't know what the adjoint solution is at t equal to 0, right? What we know is what the adjoint solution is at t equal to big T. That means we are solving a differential equation backwards in time. But is this difficult though? Not really, right? I mean, you can simply do a change of variable of t, and for example, if you can define tau is equal to big T minus small t, you can pose this equation just as an equation that goes forward in tau, right? And you can solve this equation in tau with no problem. Okay, it's just when you apply the adjoint equation in this term, in the third term, you need to transform it back into the t space to apply it. And here, I can just say this is equal to the integral of u hat of t partial f partial s dt, this whole thing times delta s. So the integral of the adjoint solution times df ds is going to be the gradient of objective function with respect to s. All right. So any questions on this? First time we go to differential equations in adjoint. Now it's clearer than the algebraic case. Yes?
Sorry, I'm just curious about one of the assumptions or things you said at the beginning,
yes,
where you say unsteady and then you're like, oh, we know something about it. I guess at t equals big T, the end scenario, does it have to be like an equilibrium? Or just because I'm thinking of this cylinder, it keeps flip-flopping or oscillating.
Right, the cylinder keeps oscillating. So the only thing I'm assuming is u at 0 is given.
Right, so you don't care if u of big T is a steady state.
I don't care. Yeah, that's right. That's right. Yeah, I don't think anything here depends on that.